Hi, this is Brad, and today we're going to be implementing a directed and weighted graph in Java using an adjacency matrix and then implementing breadth first search and depth first search on that graph using a queue and stack. So, first we need to define our custom directed and weighted graph class, which will contain an adjacency matrix of integers and then a number of vertices. The adjacency matrix will show which paths exist between which nodes, and a directed graph means that just because there's an edge or a path between two nodes does not mean that that path goes both ways. So we're going to pass our custom graph class the number of vertices in our graph. So for example, if the number of vertices were 3, then the vertices in the graph would be 0, 1, and 2. And then we'll also pass the graph constructor an array list of pairs where each pair contains a left vertex of a directed edge, the right vertex of a directed edge, and the weight of the edge. So for example, here on the right, we have an edge going from 0 to 1. So the left vertex would be 0, the right vertex would be 1, and the weight would be whatever the cost of this edge is. We have a constructor here for our custom pair class. We just pass it left vertex, right vertex, and weight, and then we set those back to our custom graph class. So we instantiate a new matrix of the size number of vertices by the number of vertices. And then we set our number of vertices before that to the number of vertices that were passed. Then what we do is we set every single element in our adjacency matrix to be 0, because next we're going to add every single edge to our adjacency matrix. So for our adjacency matrix, I'm going to print out our matrix right now to show you guys what our adjacency matrix should look like for this exact graph. So here at the top, we have our 5 by 5 adjacency matrix, as there are 5 different nodes for this graph. So you'll see there's mainly zeros, because any non-zero means that there is a directed edge from the row index to the column index. So this cell here is 0, 0. This is 1, 1, all the way up to 5, 5, and then of course you have everything in between. So this is row 0, column 0. So this would be row 5, column 0. So if we look at our graph, we can see that we have an edge from 0 to 1. So if we check 0, the 0 column, or the 0 row rather, the first row, and then we check the 1 column or the second column, we'll see that we have a non-zero value of 2. So the weight of this edge here is a weight of 2. We can look at 0 to 4. We go to row 0 and column 4. We see we have a 4 there, meaning that the weight here is 4. However, we can see that we do not have an edge going the opposite direction from 4 to 0. So if we look at row 4 and column 0, we have a 0, as there's no edge going from 4 to 0. So this is how we want our adjacency matrix to work, where zeros mean that there is not a directed edge from the left vertex to the right vertex, and if there is a non-zero value, that non-zero value is the weight. So first we initialize all of the cell values to 0, and then for every pair that we pass in our array list of pairs, we set the start vertex, which is the row, and the right vertex, which is the column, to the pair's weight. And that will result in the matrix that I had just printed out and shown you. Once we have that defined, we can print the matrix. So the way that we will print the matrix is for I starting at the top of the matrix, meaning the top row of the matrix, all the way to the 0 row, and then for every single column element in that row, we're going to print it out. So since we're actually printing the 5th row, then the 4th row, then the 3rd row, then the 2nd row, then the 1st row, we need to print out 5, 4, 3, 2, 1, which is why this starts from number of vertices minus 1 and goes to 0. But then we're going to print from 0 to the end of the row, which is why this goes from 0 to the number of vertices. So that's how our print matrix method is defined. Now we'll look at our depth first search method. So for our depth first search, we're going to essentially be searching to see if there is a path going from a start node to a goal node. So to start our depth first search, we're going to check to see if our goal node is our start node, and if it is, we'll return true. Otherwise, we're going to define a Boolean array of the nodes that we have already visited. And then as we check and visit new nodes, we're going to update this Boolean array. But we want to make sure that we're not constantly visiting the same node, especially if we have a circular edge like this one at 1, which goes back to the same node. We don't want to keep visiting 1 and be stuck in an infinite loop. So we already checked if the start node is the goal, so we can set if visited of start to true, and then we'll make a stack. So in another video I made, I described stack, which is a last in, first out data structure. And the stack is the data structure that is used to implement our depth first search. So we'll define a new stack, and then we'll push our start node to the stack. And then while the stack is not empty, we'll define a current vertex as the node that we now pop from the top of the stack. So if the current vertex is the goal, then we will return true. Otherwise, we're going to get a list of successors, which are just the adjacent nodes, for the nodes adjacent to the current node. So for example, if we look at 2, we see we have an undirected edge from 2 to 1, so 2 can go to 1, and we have a directed edge from 2 to 3, so the successors or neighbors of 2 are 1 and 3. For 0, it has an edge going from 0 to 1 and 0 to 4, so its neighbors are 1 and 4. But it does not have an edge going from 0 to 3. There's only an edge from 3 to 0, so 3 is not a neighbor or successor of 0. So let's look at how our successor function is defined. It'll return an array list of successors, which are integers. So we'll define a new array list of successors, and then for each column, or basically for every single possible other node in the adjacency matrix, we check to see if that value is not equal to 0. Remember how in our printed adjacency matrix, if the value was 0, there was not an edge from that vertex to that other vertex. Well, now we're checking to see if it's equal to 0. If it is, we don't do anything. If it isn't, then that means it's a successor, and we'll add that to our array list of successors to return until we finally return that successor. So we get our successors, and then for every successor in our successors, if that successor is not visited, we'll set it as visited in our isVisited array, and then we'll push that successor to the stack. And since a stack is a last in, first out data type, it will try searching for the node at all of the closest nodes first. whereas depth first search implements with a, depth first search will search as far as it can first, whereas breadth first search will use a queue and search the closest nodes first. So if we look at our implementation of breadth first search, we can see that it has the exact same algorithm except we're using a queue instead of a stack, because a queue is a first in, first out data structure. So with breadth first search, let's say we start at 0, we'll go from 0 to 1 and check 1, and we'll go from 0 to 4 and check 4, instead of just trying to go as deep into our graph as possible first, which is why we use a queue. So let's now run this, and we can see how I add all of the correct pairs for this graph right here. We make a graph with the 5 nodes and the list of pairs, and then we print out the matrix, perform a depth first search from 4 to 0. There's no edge one from 4 to 0, so that will be false. 0 to 3, we can go to here, to here, to here, so that will be true. And then we'll do a breadth first search. We'll go from 4 to 0, which can't be done, so that'll be false, and then we'll go from 0 to 3, which is also true. You can see how our adjacency matrix is printed out. We have false from 4 to 0, true from 0 to 3, false from 4 to 0, and true from 0 to 3. So that is an implementation of a directed and weighted custom graph class using an adjacency matrix, a custom pair class, and then implementing depth first search and breadth first search with a queue and stack class. Thanks for watching.